Welcome and thank you for joining us today. My name is David Bonifacic, CEO of WB. I am proud to say that yesterday was WB's 21st anniversary, and in those 21 years, we have experienced so many changes in the workplace, from bench seating to now COVID. Many of you also know the demand for workplace is a fraction of what it was just a few months ago. Now, many in the market are asking us about lab space, about how to reposition their existing office buildings to a life science building. Today's presentation is about answering some of those questions. It is my pleasure to introduce two of our top experts in lab design and life science, Ray Doyle and Fran Coffey. When I say that Ray is in his element when he's talking about labs, you'll understand what I mean in a few minutes. Ray leads our nationwide life science practice, and he is the reason that WB is a leading expert in lab design. He has completed over 150 lab projects throughout his career. Fran, I've worked with Fran for over 10 years now, and what I've come to respect about Fran is his energy and his ability to make complex information easy to understand. This is especially important in lab repositioning projects. I am fortunate to work with both Ray and Fran and to introduce them to you. So please ask any questions in the chat. We'll answer them as we go along or at the end. 10 minutes before we end, we will also unmute everyone. Thanks for participating, and all yours, Ray and Fran.
Thank you, Dave. I appreciate that kind introduction. So I'm going to start with some basic background just to give everybody a foothold on what we're going to talk about. And the first thing we want to let you guys in on is a little bit about how labs are different and how many different types of labs there are. And on the screen you have here is 5 different types. And in the manufacturing space, you'll find a lot of automated machines. You'll find a lot of robotics, and you'll find a lot of clean room space, different classes depending on the manufacturing that's being done. So you'll see somebody in a Tyvek suit with gloves and booties and full garb to protect the science from the person that's doing the work in the space. Chemistry lab. We have a nice chemistry lab here it's a little dated, wood casework, but it gives you the definition of kind of what you're going to see in a chemistry lab. You're going to have fume hoods, and you're going to have a lot of bench work. You're going to have a lot of work open and done on the benches. Clean rooms can range from various classifications, and we'll talk about that a little bit later. But the main thing there is that you're going to design a clean room to cascade pressures from the cleanest to the dirtiest, and you're going to make sure that you can actually have all of the processes flow. So you make sure you have the number of air changes you need from room to room, and that you either certify those spaces with particle counters, or that you design and validate the space to support that goal that's taking place in those clean rooms. So some are certified, some are not. Biology labs. This happens to be a little image of a BL3 suite. It's a procedure room in a vivarium. So you'll see the biosafety cabinet there. Clean space, typically. Cleaner space in biology. You want to make sure you have control over airflows, pressurization in those rooms, so that you can control the direction of airflow to minimize cross-contamination of particles in biology labs. Electronics labs is a huge category that can range from computers to data centers to computer research labs. You could do electron microscopes. You could end up with spaces that have NMRs, X-ray machines. So you could find yourself dealing with a lot of different research electronics equipment, and that quickly can also translate to some electronics manufacturing. So a huge variety of labs that we come across in the market. And as we talk about repositioning an office building to a lab, you have to have some understanding of what you may be dealing with from the tenant side. So that brings us to the idea of understanding how tenants want to look at buildings, right? So why do we reposition an office building to a lab? Well, for people that own the buildings, they want to have a building that they can lease, make money on right now with workplace and in a little bit of a slow period. You want to try and find ways to reposition your buildings to increase its leasability. The main thing that you have to remember is that when you're looking at a lab building, you're looking at a lab building, repositioning an office building to a lab to suit the needs of the market. So you have to understand the market. The market is a bunch of users on the science side that want to make sure they can do whatever they need to do to change their business and grow their business in the research, R&D, or manufacturing world. So flexibility is key. It's really important that the folks that live in these labs and lease these buildings understand what they're leasing. To understand what they're leasing, they need to understand, what type of flexibility, adaptability, adjustability, and expandability they have available in the building that they're looking at to lease. So when you're repositioning a building, it's pretty simple to modify, one use type from, like say a tissue suite to a biology R&D space. But if you want to make it a chemistry lab from a biology lab, now you may have to adjust the exhaust systems. If you want to expand a system, say you want to create a office space, let's say you have a building that's 50-50, 50% lab, 50% office, and you want to expand the amount of office space to increase your lab space. You would need to have utilities and infrastructure to be able to expand or change that use from office to lab. And that becomes a much more expensive renovation over time. So we're going to talk a little bit further about how these things impact the landlords, how they affect the potential tenants, how they affect the architects, and the contractors in some cases. We have a pretty broad range of attendees here with us today. The big gap, right? We talk about the big gap. It's really so that we all, as designers and building owners and owners, property managers, and understand that there is a huge gap between us and the lab tenant. Lab tenants, scientists, PhDs, they think in a way that a lot of us don't. They are actually very different in the way they see the world. They're all really intelligent, but they also see things through somewhat of a blinder. They want to make sure that they have what they need, so they have the flexibility and adaptability in the tenant space they lease. So it's our job to try and close this gap. It's our job to try and make sure we explain to them what buildings are capable of, how easily they could be converted from one type to the next, and what that costs, and how that cost can be shared across the owner and the tenant as you make this conversion from a office building to a lab building.
So that's where we get into responsibility matrix. So we use this a lot of the times. It really helps define what the different systems are and who will be providing what. So the purpose and point of this is to, outline all the different types of systems and, kind of going back, it kind of really sets the table so that both as the landlord developer knows how much he needs to invest in upfront, and then how kind of going on that expandability note that Ray just said, how the building and the spaces can be expanded to suit the tenant's needs. So in this responsibility matrix, we like to outline all the systems that we know we need, and even the systems that we don't think we need, but we may down the road. It kind of is a good roadmap for us to understand, all the different systems and who's providing what, and then what systems are expandable. It's also, with doing this, and as you are converting that office building into a lab building, it kind of, you can do it, as generic as you would like. You can kind of do it more specific depending if you're, in a city, you're in a rural office park, whatever it may be. This allows us to, basically outline and provide the responsibility of who's providing what.
That's really good, important points there, Fran. We always talk about what's important to the tenant. And it's easy for us as building owners, and most of us really have a strong rooted knowledge in how office buildings work. We all work in them. We either lease them or design them or build them. And the idea that it's pretty simple to say an office, is just office space, conference rooms, cafeteria. There might be some ground floor retail. That might be a little slow with COVID, but you may have that flexible space on the ground floor. And it may have additional amenities like fitness center. And so that those kind of building blocks, and I like the term master plan puzzle pieces because it helps me keep track of all these various configurations that you could possibly have. The real change, the game changer when you convert that office building into a lab is you start needing to figure out what you need to or can do to convert to feed and service the science community, whether it's a life science lab or in the case of the other lab types I talked about a little bit at the beginning, you start to figure out, you get different levels of biosafety containment from 1 to 4. And those can be increasing in expense and increasing in complication and redundancy of systems. So there's a lot of utilities associated with that. Chemistry is going to bring a lot of exhaust. So you're going to have a lot of elements that require additional exhaust systems and risers in the building. A vivarium is a very intense space that has a lot of air changes and a lot of additional criteria for redundancy and reliability. Cryo storage, you get liquid nitrogen tanks and freezers and different piping systems and different levels of hazard for containment and safety purge exhaust. So you could see quickly how each one of these systems and each one of these lab types starts to create these puzzle pieces, this master plan puzzle piece idea that if you're going to convert a building, you need to have some sense of what your limitations are. And that's why I like what Fran said a minute ago. In the responsibility matrix, you want to be able to not only say what your building can do, but you also want to maybe defer to the tenant cost column something that they can do. Because I always say that you can almost convert any building into another use with enough money and time, right? You can actually, you could remove floors and you can put in new structures and all of these things that you can do. It doesn't mean they're feasible. It doesn't mean they're economically the right approach for that tenant or for that building. So I always say that you need to understand the brackets, understand where the limitations are you're building, and then understand the limitations of the market and the potential, the brokers that are involved here and the PMs that are involved in this market. They know the drivers for any given region of the country. And we're talking today to multiple people in different regions. And they all have a slightly different driver from a market-facing standpoint. But it's important to understand is what you're really targeting and then know where your variables are.
Thanks, Ray. So yeah, so now as we kind of get into it and we think about, all right, how do we take this building that was designed to house workplace, and now we want to take that and try to modify it to put a lab into there. And Ray's going to get into it a little bit later with the different building types and high-rise, residential, 1-story, 2-story. But in general, a lot of your office spaces, the distribution, most of it's a single supply duct, plan and return. There's not a lot, especially if you're either in Boston or New York or DC, some urban high-rises. There's not a generous amount of headspace there. So that's one of the things that we're going to compete with. It's one of our biggest challenge when we're looking to reposition, say, your office space into a lab space. So as we get into that, we start thinking about the heights, and the heights are one of the biggest challenges, like I said. So we go into that with a single ducted system coming out of a core of a main building, and then you're going to try to modify that to now not only have the supply, but you need a ducted return, in some cases a ducted exhaust, and a lot more air needs to get moved throughout these spaces. So likewise with the plumbing systems, there's going to be wet stacks. We're going to have all over the floor, depending on the type of lab, but you could potentially have wet stacks that you can't get the pitch you need to get back to the core, so you have to create new vertical risers. So that's the one thing where by introducing these systems, as Ray was saying, the master puzzle pieces that we need to think about and incorporate this is where we can say for you, depending on your specific building and the geometry of that building and how it's laid out, well, this is where maybe we need to create a new shaft outboard of the core so that we can allow that horizontal distribution to take place, and then that constructability can happen where we need it.
I was going to say that's really good stuff, Fran, and I think the biggest piece is compromise. Knowing that we talk about ideal floor to floors, right? We talk about what it would be if you're going to build a greenfield lab building, and then you kind of start to chunk back. Where are you? What's your office building floor to floor? Where does that fit into an ideal scenario? And when you're looking at repositioning, you can start to understand how you need to define those zones and define your flexibility. So if you understand your limitations, you can understand the limits of your flexibility. And this is one of the first pieces of an evaluation to convert, is to understand all of the elements that you have to have in the ceiling, and then compromise maybe on ceiling height or bulkheads, or maybe in equipment spaces, you're going to run your mains and you're going to have a lower ceiling. So there's options to communicate these things and transmit ductwork and systems through a building and still make a very nice space in the end. You can still have some areas where you have some flexibility with ceiling height, but you have to really do that master plan, right? That master plan conversion has to be thought out.
Yeah. And it's kind of going back to that responsibility matrix and the overall goal of the repositioning with what are we trying to do here? What are we trying to accomplish? What's the most important thing for those potential tenants? And in that case, that's where we tend to lean on the brokerage community to kind of tell us what these lab tenants are looking for, so that they can help us drive and make the decisions that are going to be the best payback for your investment on this repositioning.
So mechanical systems, we talk about these a little more when we talk about repositioning, mostly because they are the biggest element that is in to kind of impedes your progress, whether it's physical space for air handling units or chillers, or it just ducts themselves in the ceilings or transmitting airflow from one floor to the next. So the kind of this master plan puzzle pieces idea continues on, right? So in an office space, you're really just looking at envelope loads and interior heat gain, which is standard office equipment, right? You got a computer or a laptop, and you might have a printer every so often and a copier every so often. So those loads are very well known, and everybody understands what you're up against. But when you get into a lab, you can get hugely varying electrical demand, and that electrical demand is driven by the mechanical equipment. So the actual heat gains in the space are defined by the lab equipment that the users need to house and need to operate to function to produce and do their science. So you find yourself up against a large varying load. You could be anywhere from 6 watts a square foot to 30 watts a square foot in a lab heat gain, and that's a pretty dramatic swing. You find yourself looking at specialty equipment that could be point load heat exhaust, and you might have a very high sensible load in a given equipment space, and you have to deal with that. Air change. Yep. Sorry, Dave. Go ahead.
No, there's a few questions before you move on to this from this slide. Let's circle back to some questions. So keep going and tell me when you're ready.
Okay, I'll just real quick jump to the end of this one. But the main thing is that you got to make sure that as you define your equipment sizes, you make sure that you understand the needs of the space, and that's the needs of the science. So you could have single pass air, you need energy recovery depending on how much 100% outside air you have. So that really defines a lot of the big equipment, and that we'll talk a little bit later about how some of those things can vary in application.
So Ray, one of the questions I'm going to paraphrase, but has been such a concern on energy code today, and all these systems seem like they cost a lot of energy and power. How does the energy code relate to, and how do they impact lab design in life science buildings?
It's a great question. And I always go back to, I use the analogy for the folks that maybe know different industries. A lot of people know office space and lab space. And office is pretty well defined by the code, and they limit how much heat gain you can have. But they can't really limit is how much process heat load or process load you have. So for example, in the case of a data center, they can't tell you if you can have equipment on your data center floor at 30 watts, 40 watts, or 100 watts a square foot. That's a process load driven by the business at hand. So those become zeroed in the energy code. The building envelope, the lighting, everything that's controlled by the code is still required, same as it would be in a lab. So any of these process loads would be excluded from that energy demand. To the second half of that question, Dave, the energy requirement to try and reduce and conserve energy is important to everybody. So if you can use low flow fume hoods, if you can use lower energy devices, if you can increase your energy recovery to maximize, the heat recovery or energy recovery from the exhaust air back into the supply air, those are the ways that we can optimize and make buildings more efficient. And from building to building, that may depend on how the leases are structured for the folks on the broker side. And you have to understand that when you make a conversion. How are you doing your leases? And we can talk a little bit about that as we move forward.
Hey, Ray, just one more thing to add on to it. Just speaking of energy codes in general, even as it applies to office spaces, I think, over the years, the energy codes have been driven down. Everything's been tightened up. We're trying to save energy, which is a good thing. But it's to the point where some of the ventilation rates and indoor air quality, I think, have been somewhat sacrificed. And in light of this pandemic, I think we're going to possibly seeing some of these energy codes, some of these restrictions lifted, even outside of labs, possibly in some office spaces, to make sure that, these spaces that we're living in a lot of our lives, have the best quality possible.
And there's Ray, there's a question here. Are there any examples of high-rise buildings which were repositioned into a life science use in New York City or other domestic cities, ? Are there predominant lab uses that are trending today in urban locations?
I think it's another good question. And a lot of the high-rise buildings tend to go more to the biology side and less on the chemical side. So there's less chemistry in general being done, chemical research. But it's not to say there isn't any, right? There's still tenants out there that are looking for space that are on the little heavier on the chemical side. But in general, the high-rise buildings are easier to convert to lab or life science-driven spaces because they don't have the code limitations of how much chemical they can store on the upper floors. And they have less issues with adding fume hood exhaust, which requires additional penetrations through the floors in an existing building and a repositioning. So those challenges come up in repositioning. If you're doing it new, you could address those a little easier. And again, we'll touch on that in a slide in a few minutes.
I want to stick with the mechanical questions here. Is 100% outside air mean it's a single pass for general R&D? Do you recirculate?
That's a great segue, Dave. I'm going to jump into that right now, if that's good. So speaking of that, there's different systems to think about in kind of going into the building HVAC concepts. And when you're converting that building in the mechanical system from, say, a office space to a lab space, you have to think about what's the most important and how to build in that flexibility. So, as we go into these types of systems, the 100% outside air system, this would be the type of system this is driven by the ventilation, or I should say the exhaust requirements for the lab spaces. So this would be a single pass. As that air goes into the space, it's one pass and it's on its way out. And this system could be, just in a portion of the building, depending on how those splits are. Sometimes we're seeing 50-50 from office to lab space. Sometimes it's 60-40, so whatever it may be. But there's flexibility where you kind of have to understand what's driving the airflow, what's driving the load. So in going to a single pass where it might be more of a load-driven reasoning, this would be a single pass where you could actually have this air handler both serve an office space and a lab space. So you can kind of repurpose some of your, say, original base building systems, and you can use that flexibility and add onto it where you need to help support both spaces.
That's a really good comment, Frank. 'Cause I want to go back one slide because I want to pile on to what you just said. So as you just described, the idea of being able to repurpose an air handling unit in an office space to be able to share the air between office and lab. And in some cases, you maybe have a single pass air where you dump that air back outside when it goes through a lab. The 100% outside air lab spaces are becoming less frequent and only based on real need to contain the airflow. So chemical fume hoods, exhaust devices, you'll find too that places where you have vivariums, where you have isolation rooms, or you have medical facilities where you have, let's just say, COVID patients, you might have an isolation room where that air is only coming in once and going out, never gets recirculated. So there's a lot of cases where you can supplement the system, as you said, Fran. You can add this type of system, 100% outside air system, if appropriate, to portions of an office building or a repositioning project. So those are nice ways to look at both of these two systems and tools to modify an office building.
And Ray, can I get a question in here from our audience? What is a recommended minimum air changes in life science?
That's a good one. So there's no specific minimum. I mean, I've seen labs down as low as 2 to 3 to 4. I like a 6 air change rule as a general plan, but you can work from that, slightly down from that. You could have an unoccupied air change rate lower than that. You could have, low, what's the right word, containment space or hazard space where you can have even lower air changes as long as you can maintain your temperature control and you do your containment within devices, whether it's a biosafety cabinet or a fume hood. The main thing you want to be concerned with is the requirements of the code. So when we talk about air changes, there's standards that define minimums. So in an animal facility, you'd have a minimum of 10 air changes. In a fume hood, you have a minimum of CFM per surface area inside the fume hood. So that's going to define a minimum. The higher end is based on safety and the hazard level based on a few things, right? The code is the minimum, and then you usually have to work with either an industrial hygienist, or you sometimes would end up working with, for a bigger end user, they might have a internal safety officer or a health and safety department where you would want to evaluate all of those criteria at the beginning of a project working with the tenant. So they vary widely. The main thing is minimum is the code, and then work from there with the tenants and the building owners to establish the best plan for the building.
Right. And then one other question, is it typical to have the supply air from one source serving both office and lab space?
And I would say probably not typical in big pharma. Big pharma, they're usually going to look to isolate everything, and they have a higher level of risk because they're probably farther down the road in research. So if you look at a beginning processes of most companies coming out of research or incubators in the higher ed and university spaces, they're a little more willing to have a little more variation in their science. They're usually willing to take a little more risk for cross-contamination to save money. So you'll find a lot of the startups will have a lot more of the return air associated with their mixed spaces, where an office space may feed into a lab space, like the single pass air diagram that you guys are looking at now. So that can actually be a way for them to save money, initial capital as they start their businesses, and then look towards that flexibility or adaptability that if they see themselves in 5-10 years evolving from R&D to maybe light manufacturing or clinical trials or whatever their science may be driving them towards, they can start to look at other options.
And then
So
can you lower air exchanges in office but bring in only outside air?
Lowering the air changes in the office to bring in outside air would be one of those in a DOAS situation where you might bring in the minimum amount of outside air to a building. And that's a good question, Dave, because we talk a lot about air systems in this presentation, and a lot of it's driven based on that's the biggest space constraint that you're going to have when you convert an office to a lab. But when you do a DOAS type system where you might bring in just outside air, you could do heat rejection through chilled water, condenser water. You could do chilled beams or fan coil units, a couple different ways to move heat throughout a building. And it needs to be studied when you look at each option, when you look at each building to convert.
And Ray, for the benefit of everybody, a DOAS is a dedicated outside air system. And also there was a question about acronyms. In our invitation, there was actually a glossary attached to simplify some of these acronyms. I know life science folks, Ray, have a lot of acronyms. So there's a glossary attached to our invitation for everybody to refer to if we kind of lose you on that.
Yeah, thanks for doing that, Dave. We often find ourselves talking in acronyms, and I might lose some people, almost worse than the government in some cases. So yeah, next topic, really. So this is where we talk about the difference between a 1 through 3 story building and then a building that's 4 stories and larger or higher. The real advantage, and this really happens in most of the urban edges, right? So you get into the idea where you have a little more sprawl, urban sprawl, and it gets out into the suburbs, and you find yourself looking at low-rise buildings, 2-story, 3-story, warehouse that might be office space that could convert easily to lab. And the great part about those building types is that they're easily managed by the landlord, easily converted to lab because there's more roof space per square foot of leased space. So when you look at these conversions, you can define roof space and actually have dedicated equipment to feed each tenant, which is good for a lot of reasons, right? Now the tenant can either own and operate and manage that equipment, be responsible whole, like a triple net lease where they can manage and own that equipment. Even if they didn't run it and manage it, you could still now manage the bills and the utility costs in a much easier way. So a big user has their own equipment and it's dedicated to their space. And there's rooftop space to do that. And containment through exhaust is a lot easier as well because you don't have to go through 1, 2, or 3 stories, which is a lot less disruption to the building. When you get into the 4 stories and up, you can quickly see as you increase in height, the limits and how much roof space or equipment space you may have to a given leasable square footage below. And like an office building, you might find yourself having a central air handling unit. It might be a central DOAS unit with a chiller that feeds risers. It might be a dedicated outside air unit or manifolded outside air units that feed multiple floors, just like you would in an office space. In those cases, I like to look at things where you can have airflow measuring stations at each floor. So you could still sub-bill each tenant for the use of the energy at hand, but you end up having to be an energy or building manager that's going to be willing to do that in a high-rise building. So those are some of the challenges. The idea that you manifold those systems is really nice. Think of the roof plan where you might have space, kind of this master plan puzzle pieces idea again, that if you had 3 air handling units that fed 10 floors, if you were fitting this conversion from day one to day end, and day one you might only have 2 or 3 tenants signed up, you would only have to put in one of those air handling units. You might have to pre-invest in the riser, the infrastructure to distribute that air all the way through the building, but you wouldn't have to buy all 3 air handling units until you added those leases, floor at a time, half a floor at a time, whatever building block you wanted to lease, but you wouldn't have to pre-invest all of that money in all of that equipment day one. Similarly, you do the same thing on the exhaust side. You can build those modular fan systems on a manifold and have that riser feed down multiple floors. Talk about that in a minute here as well.
So so then we get into the electrical systems and, thinking about, what needs to get done, what needs to be thought about as we're trying to convert these, say, office spaces and office buildings into lab spaces. So, typical office space, there's not too much, normal power distribution. There's life safety power typically in the high-rise buildings. When introducing a lab, there's some other things to consider. Some of the power is legally required to have the backup power in place, and that's outside of, let's say, the life safety. There's standby power, UPS power, medium voltage power, and then some people care about power quality. So, at this point, this is kind of where we like to think about and look at the responsibility matrix to figure out what makes sense to put in day one and what makes sense to defer that cost to the tenants. Because you don't want to start putting in centralized UPS and running power all over the building for some tenants that might not have that requirement. But it may be a good idea to invest in a standby generator so that that's in place and that will be attractive to a potential lab tenant. And then some other things that when repurposing office space into a lab is the actual distribution. We did this one project in New Jersey where they didn't have like a typical bus duct riser. It was just conduit feeds from the main switchgear up to each floor with disconnects. So in that scenario, that worked for the office building because office loads are pretty consistent from space to space. But once you start getting into different types of lab users that have different power requirements, it may be worth that investment. And in that project, in that case, it was worth the investment to, demo those feeds out and put a new bus duct riser in place so that would be that built-in flexibility for the tenants to take as much power as they want. Another thing to think about too is the kind of going on the same terms as or line as Ray is thinking about, in a typical office space, you may just bill in that power per square foot into the lease. In a lab with those loads varying so much, it may be more beneficial to put some type of sub-metering in place, or so that that's incorporated into the lease, so that that there's a check meter in place, so that the tenants can get compensated for that high usage.
Along those lines, Ray and Fran, there's a question. What are your thoughts on using district energy as a versatile tool to reduce restrictions on converting office to lab space? For example, no need for more chilling capacity or heating capacity, and no need for new steam generation for sterilization, etc.
Not sure I understand the question.
Basically,
clearly.
I would say that this would, if you didn't have your own infrastructure, using a district energy source.
So if you were going to connect to a city energy source to provide heating,
that's how I interpret it.
No, okay, that's good. So yeah, if you were in a city where they had steam available and you could convert it and put an absorber in and use that steam to heat the space, you want to take advantage where that where the first cost savings, kind of maybe outweighs the initial capital for your tenant or for your conversion. So a definite detailed analysis would be required to say, how much power do you need? What are you converting and how much heat do you need per floor in your master plan? And then balance the cost, your capital investment for that conversion against using the utility steam sometimes in the cities. I find that a lot of the utility steam in the cities is a little expensive. So in the long run, you're sometimes better off by putting standalone systems in. But again, you got to do a capital investment payback analysis to understand project to project if that approach makes sense. I don't think there's a one answer fits all in that case.
Yeah, I think that makes good sense, Ray. One other thing I want to touch upon as we've been doing these repositionings and looking how to convert them is, especially in some of the older buildings, older vintage buildings, it's been kind of a little bit eye-opening, even from our perspective, to see that, as we're looking at the loads and the power available, that some of the distribution, even on the floor level, is able to handle the capacities that these tenants are requiring. And if you think about it, it kind of makes some good sense because a lot of the infrastructure in place, these were designed with fluorescent lights, with computers being way less efficient. So as you start to add up, and as well, all trying to conserve energy and use less of it, that these systems are actually built to handle some of these increased lab loads. Now, depending on the lab and the space and the demand, it may not be able to, handle it at all. But in a lot of scenarios, some of these watts per square foot are in place and in line with what these lab tenants are looking for.
Yep. So you can balance that out in the responsibility matrix to say that you have 60% office and 40% lab, but you only have 10 watts available per square foot in the lab, and anything above that they would need to pay for as a tenant upgrade. So you got to create the limits in that responsibility matrix, which is the other reason that document is so important. So on the plumbing side, we end up with a lot more risers, a lot more systems to evaluate. And again, they're just more puzzle pieces. You need to make sure that you allot for the space requirement for each of these systems. So, and it's kind of simple, right? You go into an office building, you know that the rain sheds off the roof and that the toilet's flush. And in the case of an irrigation system where they might have a nice garden, everything's growing. In California, you might have a gray water system requirement to meet the code there. The main thing is that you have to understand in a lab, there's another 10 or 15 different possible systems that you're going to have to manage and either provide for the tenant or as part of the responsibility matrix, typically require the tenant to fund and manage and build. But it's good to identify all these systems in that matrix so that you don't lose track of things. Things that you forget about can be pretty important later on. If you say they need central gases, cylinders in a lab are simple, but as soon as you have a manifold, you need a closet. As soon as you have a central tank or a tank farm, now you need a space outside your building to manage and maintain that and secure that. So it can be a pretty decent sized puzzle piece from a building owner standpoint. But the lab user, the guy we talked about at the very beginning, he just wants to know when he opens the gas turret for nitrogen or that he gets it. He's not really worried about sometimes how it gets there. So it's important for us as designers and building owners and conversion folks in the market to make sure we address all these pieces. But some of the more challenging pieces that you kind of have to think about up front are things like lab exhaust. Lab waste. And the lab waste is a permanent riser that typically should be installed at the time when you do the lab conversion. Because once you start fitting out the floors, now you're looking at setting up new risers through other tenants, and that's going to be a lot more complicated. So when you do your initial conversion, when the building's empty, you want to get those risers in place. You want to make sure you have a waste treatment room, whether it's a passive treatment system or an active treatment system. You have space in the room in the building for that, and you have the outfalls coordinated with the civil so that you're not putting in a lot of pumps where you don't need them. Always want to avoid those pumps to save yourself the hassle and headache of maintenance in the future. And so that's a real important piece. Things like tempered water systems for eye washes and showers are important if you're going to have more chemistry. A lot of times that is in the tenant responsibility column. RODI water falls in that same category. It's easier to do in most tenants in the space, at the bench, or in a small closet in the leased space. Similarly, you would do that with vacuums and compressed airs. If you had one tenant, the build to suit, you might consider putting all these things in as central, but typically they're going to be provided by the tenant in their closets, in their cabinets, in the casework. Cryogenics is a whole nother game. You're going to have to deal with that when you get into a specific tenant, but you want to make sure that if you're going to plan for the ability to do cryogenics, are you going to have a liquid nitrogen or nitrogen tank outside to manage that particular utility? So you want to have that in your master plan. When you're showing people your building, you have the capability for them to do it is a nice leasing option for some folks.
Ray and Fran, I'm going to slip in a structural question here. I know we're not structural engineers, but do you know what live load capacity range do you recommend for lab floors and or lab roofs?
Yeah, so on the live load and dead load categorization, we want to make sure that we evaluate the conversion first. The main thing is to understand, is it code minimum on the office side? So if you're going to look at a building and convert it, you want to be able to make sure that you can first know what you're up against, and then know what you want to get to when you're dealing with equipment labs, as I described earlier. They tend to be your higher structural loads, and where you have and sometimes you'll put in an NMR in different spaces in a building. You're going to find yourself working with the structural engineer, and he's going to actually paint yellow lines on the floor and say you can't store anything in these spaces. He's going to limit where you can store anything other than a live load, which would be a walking load, somebody walking through the space. So those all need to be categorized by a structural engineer, Dave. So I'm going to defer in most cases to the structural engineers in that case, and we can help partner with those folks in the marketplace. We have a lot of great structural engineers we work with, and they would help us through an evaluation in the conversion to make sure that you have the limits of what you possibly can do for your tenants.
Okay, so here's a plumbing question. My tenant says they will only put water down the drain. Why do I need a separate lab waste and treatment system?
Okay, so in typical, not all jurisdictions, let me say that. In most jurisdictions, you're safer to separate it because you can be penalized by the local water authority. Now, if you don't know who's putting that stuff down the drain and the water authority is testing it at the street or at the manhole, he's going to find the building owner. And then the building owner is going to have to try and figure out who in his multiple tenants is responsible for actually creating that breach in the limits. And that's real challenging. So it's a jurisdiction criteria. Some are very lax, some are very strict. I think, Fran, we were talking about a company you experienced.
We did it for a large coffee manufacturer we do a lot of work with. So they actually were just doing some testing, and they were dumping the used coffee down the drains, and the MWRA actually made them put in a treatment system because it was so acidy. So it's kind of pretty eye-opening. It's something that no one would ever really think about, just testing out coffee. But that's something, it depends on the local requirements. So it's something to be mindful of for sure.
So Dave, when we start jobs, we do these conversions. I think it's important to note that we want to meet with all of the utility providers. We want to meet with the water authority and the waste authority and the power companies to make sure in the conversion, what are we capable of? What is the utility going to have readily available for us, and what are their limits? Because in some cases, if you're in a building that's remote to a distribution system, whatever it may be, gas or electric, or there's penalties for waste distribution, we want to know that when we do the conversion. So our landlords that we're working with, our building conversion folks, understand where their costs or hidden costs may be. So it's helping them understand what we call known unknowns. We don't know what the limits are, but we know who to ask and how to get you the right information so you can make good decisions.
One more question, guys, on this, since this was asked twice. Can you explain the difference between single pass air and 100% outside air? One is more beneficial toward chemical users versus the other benefit. Who's the other one beneficial for?
Here, Ray, I'll give you a little break here. You've been talking a lot. So so 100% outside air system is a strictly a one pass system. it's going to be less efficient than, say, the single pass. At least in the single pass system, you're able to recover some of that air and recirculate some of that conditioned air in this setup, where it's kind of shared from office space to lab space. And I think the other piece of that question is what's driving that. And I kind of touched upon that a little bit, but with taking a look at what's driving the amount of air we're trying to pass through here. And sometimes, like in a chemistry lab building, it's going to be that amount of exhaust air and the makeup air required to keep the building pressurization in line. Whereas, if you went to a single pass, it might be more of a load-driven requirement that's going to, drive how much air needs to get into the spaces.
So that's really the main point. That one of containment for exhaust-driven spaces will drive 100% outside air, and that's exhaust-driven. So when you have 100% outside air, it's typically exhaust-driven, and when you have a single-pass air system, you make the decision it's more load-driven, or a higher percentage of the building is load-driven, and then you try and optimize energy, based on coordination with your tenant and building owner, your cross-contamination concerns, and then you make the decision to do more single-pass.
All right, I'm going to keep driving this here because I want to make sure we have enough time.
Running up against the wall here on time?
Yeah, no, I think we're doing it. Yep, go ahead.
No, that's good. So in the office building, we talk about just ROM numbers. These are kind of variations across the country, and generally there's a pretty good range. But between 40 and 100,000 square foot office building, you're going to range between $200 and $300 a square foot, and your fit outs can range between 80 and 130. There's outliers in both cases, depending on the skins of your building and how expensive your finishes may want to be inside. But it's a pretty solid range in the middle. So when you get to labs, you find yourself in the same categorization of building size, and you really aren't spending a tremendous amount more money if you're going to build a building from a core and shell standpoint from $200 to $400 a square foot. And the reason it's not a lot more is you're not typically going to buy all of the infrastructure. You're just buying heavied up structure. You're creating a master plan of puzzle pieces that allows you to do shafts and openings where you need them in the structure, but you're not buying all of the mechanical systems. You're not buying all the plumbing systems. You're not buying all of the electrical gear in a lot of cases to fit out the labs. You do that once you have your tenants on board. And that's why the tenant costs can range considerable, but they can also increase in cost. But if we do that in most cases in our conversions to make sure that you can defer your capital investment to the tenant once you have them on board, and you can include all of that in their TI. And that TI would be based on the science that they're doing. So one tenant may be simple BL1 R&D lab, which you can do relatively inexpensive. But if you get into, BL3s or BL4s or manufacturing with clean space or high-end equipment, you could see how quickly you could jump even past the $500 square foot mark. I've seen labs in the range of $800 to $1,000 on the very high end. So those things need to be considered when you're working out your leases and understanding what the conversion is going to be. This case study is just to give you guys a simple base load on a typical floor plate in an office building of a 30,000 square foot building. On the worst case scenario, you typically would see, not absolute worst case, but in most of the retrofits from office to lab, you're going to see something in the range of about 50% lab, 50% office. And in the lab, we're going to range about 2 CFM a square foot for heat load with a ducted system. That'd be different if you were doing DOAS with chilled water. But again, worst case scenario for space constraints. And then 1 CFM a square foot. And the thing we want to make sure we account for, and this is important when you talk about your master plan for your conversion, you want to consider about 1,000 CFM of exhaust per about 1,200 square foot of lab space. These numbers can vary a little bit, but you also want to make sure that you don't exclude tenants that have lab exhaust requirements. Most biology companies have a fume hood every 1,000 to every 2,500 square feet. They have some need to do chemical process. So this is just simple diagrams to understand how in an office space in the lower level, you're going to have a supply and exhaust riser in the middle. In a typical office building with a rooftop unit, for example, you're going to have a supply and exhaust. You'd have a VAV loop, and you'd have general plenum return, as we described at the very beginning in an office space. In contrary to that, you look at the lab configuration. You could, if you go airside solution, you're going to find yourself with sometimes twice as much supply and exhaust space, so maybe twice the risers. And then you're also going to have some dedicated exhaust on the perimeter. And the reason we push these out to the perimeter in a conversion is that there's the reasons that Fran talked about at the beginning, is this idea of trying to finger systems together so that you don't have the exhaust risers in at the core. Because if you can imagine crossing the 3 or 4 major duct systems, if you have a hazardous exhaust, a lab exhaust, a return duct, and a supply duct, 4 duct systems trying to come out of here and serve 30,000 square feet, you'll never get there. You'll have no ceiling height at the core. It gets really low ceilings and really complicated bulkheads. So there's a lot of challenges.
And then all of our architect friends will be very mad at us, and we don't want that. So, another thing to think about too is the code. Luckily, Andy Shanahan started the our code consultant group about a year ago, and we've been very lucky and benefit to having him and leaning on him. So, the typical codes, building life safety codes apply to lab spaces in general. It's good to understand NFPA 30 and 45, which is a little more stringent. Every building's different, so everything kind of needs to get analyzed and assessed. Some of the things to be mindful of is when you are thinking about going to a high-rise building, the higher you go up, the less flammable storage you can have. I believe if you go from like the ground to the first floor, it's like 40 times. You can store 40 times more flammable storage down low than you can above 4 stories. So as you get into that, it's you're definitely limited. But it's once again, it's kind of that's another one of those puzzle pieces that you need to think about up front, understand and define up front, so then it can be planned for.
So as Fran said, you get into this idea of hazardous exhaust, and really it comes into this category of fume hoods or hazards. And you need to make sure when you do these conversions, you have an understanding of how many of the floors you want to have the capability of storing chemicals, and how much you want to have the ability for your tenants to have hazardous exhaust. It's a real important factor, because if you have these systems in a high-rise building, you have to understand that you have to isolate the riser, the hazardous exhaust riser from, let's just use the example of the 5th floor. From the 5th floor to the penthouse, that riser would be continuous. You could have multiple connections on the 5th floor, but the riser would go all the way up untapped to the penthouse or the roof. So on this little diagram to the right, you can see how you'd have multiple risers feeding multiple floors. And that's why in that plan diagram, I was showing multiple exhaust risers. The key here is to make sure that in the conversion, you have the structural capability to create these holes. Or if it's a limitation and you don't want to spend that money, you want to defer that cost to the tenant and have them pay for that structure. The key is planning it for the flexibility at the beginning of this conversion from office to lab, so that you don't paint yourself into a corner and have to run shafts through an existing tenant on the upper floors. Because all too often the brokers know everybody wants to move into the upper floors first because that's the most desirable view. But then when you put in your lab tenants down below and you got to crank risers up through it, now you're putting holes in their floor, in their office space, in their conference rooms and the like. So challenges of making sure that as we talk about it, bridging the gap, bringing the lab folks into this discussion, understanding what they need, why they need it, and how it impacts a conversion. So if you make sure you have this master plan puzzle piece and have all the pieces on the table, I say it's just a messed up puzzle, and let let architects help you sort through the puzzle pieces in the conversion, so that you create a good utility matrix, responsibility matrix, so that the tenants know where their costs are and the landlord knows where their costs are, making the leasing a lot simpler, the conversion a lot simpler, and making for successful projects in the long run. That's our big goal in getting through this presentation for you guys. So hopefully you have a few minutes. We ran a little over, but hopefully you have time for a few questions.
So I have a question. Do you have a problem with connecting all of the exhaust from the building, including the fume hoods, with your office exhaust, basically for one big, nice exhaust all the way up?
That's a really good question, and the issue is the code evaluation. So if you have something that's categorized as a hazardous exhaust in the code in NFPA 45, you cannot combine that with the toilet exhaust or the general exhaust from a lab space. It has to be isolated and taken out of the building separately. So did I answer your question? You can't really combine them if it's a hazardous exhaust. If it's general exhaust, if it's a biology lab, for example, you can combine all of those exhaust systems and run that through an enthalpy wheel or heat recovery device and optimize energy savings. It's when you get into the hazards. And let me explain real quick, just for clarification, because I'm glad you asked that question. In the case of the hazards, the real reason is that you can't have fire dampers in hazardous exhaust. So when the firefighters come into a building to save the workers, they leave the fume hoods on. They want that exhaust, those chemicals inside of the hoods to get out of the building through that riser. They don't want a fire damper to close that duct, backing those chemicals up into the space and hindering the rescue mission. So that's the real reason. It's a life safety issue for the firefighters that are going to come into the building when there's an event.
But assuming that you don't need to have dampers, if you design a thing that you always connect it directly to your shaft, going those 2 feet up, and I mean, assuming that dilution is the solution, can you connect the fume hoods to the general exhaust? And is there a different understanding in the codes between East and West Coast?
I think you need to make sure, and now I get what you're saying, you need to make sure when we do these conversions, we meet with these local code officials and the authorities having jurisdiction and define exactly their interpretation of NFPA 45 and NFPA 30, because I have seen in some jurisdictions where they allow you to use subducts or something to that effect in special cases. But if you follow the letter of the intent of the code, you're not allowed to take a fume hood and run it into a general exhaust and have that feed multiple floors. So if you go back to that diagram for me, Fran, just for real quick reference. So you would have a separate exhaust system than this if you had general exhaust or room exhaust. These exhaust risers would strictly be for what we would call hazard exhaust as defined by NFPA 45. And that's why they're separated.
And by that, you would mean anything that comes out of the hood versus anything that's just room exhaust, general exhaust out of the room, correct?
Correct. And here's why, just to take one step deeper into this puzzle. The fire rating of a floor for safety, for fire hazard, is 2 hours in most buildings.
Right.
If you take a duct that goes through that without any dampers at all, now you've broken the 2 hour rating. If you run this duct in a shaft, its own shaft, like the image on the right, from the 5th floor all the way to the penthouse, now you haven't broken the 2 hour rating. You've essentially made the 2 hour rating the vertical shaft.
Right.
And that's the safety. That's where the code official has to understand the interpretation. He has to agree to the hazards you're using in the lab and then define it as a criteria for that building. And then it becomes part of the building owner's mandate to manage. Once you do that conversion from an office to a lab, then they need to understand, as they fit out tenants, they understand the rules that are governed by the code and by that local jurisdiction.
So the driven force is the dampers, not anything else as far as the concept.
Yes.
Correct. The dampers are the main purpose, but really has to come down to the interpretation of hazardous exhaust versus general lab exhaust. I'm of the opinion that you should separate those in every case so that you can avoid having, huge ducts run up through the building. You run a lot more shafts and fire rated shafts if you do them dedicated per floor. You need to make sure when you lay out your conversion, you understand the limits of the building structurally so that you can make good decisions. That's the main point I think we should to stop on. And I'm happy to follow up with you and we can go through more specific scenarios, maybe with the building that you're talking about. I'm happy to take it offline and go into it in a lot more detail.
Well, here's another question that comes up a lot too. It has to do with in a fire emergency when the alarm goes off and the HVAC equipment shuts down. Do you want the fans to shut down or not for the lab exhaust? Because you mentioned in earlier in the conversation about keeping them on to dilute or exhaust all the chemicals out of the building. But then you've got the fans running and no supply air, so that those fans are going to be pulling air from somewhere, whether it's through the office spaces, through other spaces, if they're not shut down as well. So what's your...
Well, I'll help with this. I think it's too dependent on what the smoke evac system sequence of operation for that building is, right? Because it's going to be different in every building.
Right.
In most cases, you're going to be doing the sandwich approach there, where you're going to pressurize the floors above and below, and then you'll exhaust the one of the floor has an event on it.
In a high rise, yeah.
In a high rise, correct? Yeah.
But in
a
a
high
low
rise.
Yeah, Dave, if it's in a lower rise configuration, we typically will have the outside air dampers on the air handling units left open in an emergency situation.
Open, that's what I thought. Yeah, that's
so that they can make up the air. And again, it's for the life safety of the safety firefighters that come into the building, so that air does come through. And then once they've established control and they can shut things down and feel things are safe, they will.
No, that just came up on a question on another building that I said the same thing, that the damper should fail open, the exhaust needs to run, and because we were getting into a smoke evac sequencing issue there. That was what I thought. So thanks for the...
No, it's a good point. Most people think outside air always fails to the closed position, but in this case, you'd want it to fail to the open position.
Yeah.
So any more questions? I think, Fran, if you could put your contact on the last slide, please, up.
Oh, yeah. Thank you.
So I know there's, again, questions that we are going to be following up with a glossary, a follow-up email. There's going to be a link to this entire presentation for a recorded for anything. And please feel free to reach out to Fran or to Ray with any specific questions. And I know there was one question which I'd like to follow up separately with someone who asked about the hazards on codes regarding the hazards and the hazardous materials. I think that's a whole lecture by itself. Mm-hmm. So we're going to reach out to anyone who has that question. And I appreciate everyone coming and participating in this. And I think it's an exciting time for life science and lab work, and look forward to keeping in touch. Thank you, everybody.
Thank you.
Thanks, guys.
Thank you.
Very good.
Thanks, guys.
Thanks, guys.
Thank you.